In the previous lecture, we have discussed the main concepts of the structural mechanics, which is strain. So what is strain? Strain is when you take a spring, for example, and then you try to extend it, so the amount of relative increase in the size is a strain. The stress is similar as the pressure in liquids or in gases, but this is the pressure in solids. And the other concepts of strength, so the stress in which the material starts to break down, and the toughness. It's interesting. Almost both of all these words as an STR are quite difficult to switch off between them. And today I would like to give you some quests so that you feel in the shoes of the investigator to see how you can use these concepts of structural mechanics. So I'll give you 30 seconds to discuss it within the three of you. And here is the example, what happened to the Liberty ships during the Second World War. So it turned out that most of these ships, maybe almost all of them, were collapsed in North Atlantic, but not in the South Pacific. So please discuss what was the reason, why did they crash?
What were the three words again?
Pardon?
What were the three words again?
Stress, strain, tough. Also, strain, stress, strength, and toughness. Toughness is how the material is resistant to fractures. Okay, so I'll give you 30 seconds.
Maybe there's a difference in weather conditions.
Yeah.
And so that's
Colder water.
affect the toughness
Yeah.
of them.
The fracture. Yeah.
Yeah, how much they fracture.
Yeah. Sounds good to me.
Okay, so looks like you have some version.
So we said that there's colder water in the North Atlantic and colder weather conditions, which would affect the toughness of the materials on the ship and increase their fractionation.
Yeah, it is an explanation that indeed in cold water the material becomes more brittle, like a glass, and these ships were made of not a good steel. There were some mistakes made, and when they welded the ships, there were some micro cracks, and these micro cracks started self-propagate and causes the collapse of the ships. And now I would like to give you some explanation of why the cracks can propagate and become self-propagating and destroying. So if we have a look at the material, we'll keep the size of it fixed. And this will be assumed to be energy enclosed system. We'll introduce some scratch or fracture. And what happens is with the scratch, there is some energy comes in. So we will call it the energy of the scratch. And it's proportional to the size of the scratch, which is L. And it's interesting that this energy comes with a minus sign. I will describe it a little bit later. So when it happens in the material has to compensate this extra energy. So what it does, the strain appears in the material, and the way the material compensated, it relaxes some stress. So usually what we see, the edges of the material start to go to the side, and this is typically the area where the strain appears and compensates this extra energy. And this one is the energy of the strain. And it is proportional to the area of these sides of the triangles. So now, if we plot it on the energy diagram, we would see that one of the energies, which is due to the scratch or the fracture, goes linearly down, but the other one is quadratically goes upwards. So what happens if we now try to sum up these both energies, we'll see that at some point, our material will be will no longer be able to compensate this with the stress to compensate this with this fracture. And this is what is called the critical size of the fracture. And as soon as you reach this size, which is different for different materials, it starts to propagate. And so this could be dangerous, and you need to take it into account when design the stability of the mechanical things. And today I would like to show you just an example of how we can use it for controllably cut the silicon wafer. And later, after this class, you can come and try it. So, for example, this is a big silicon wafer, which we typically use in nanotechnology to prepare some samples. And these are the small ones, which you can break it in. So what you can do, you take it, actually this is a crystal, and when I make a scratch, just a small one, and then I can apply some pressure, and you can see how a small scratch can almost like cut it straight. And you can continue cutting it until you get the small nice pieces.
Okay, that's time. Thank you. Okay, comments?
I liked the kind of bookended nature where you had like a real life example and then like equations, which for some people can be overwhelming, and then you bring it back to this nice visual example for people to interact with. And I think especially for a lot of board work, it's nice to have those things to break it up.
Any comments?
Yeah, I mean, I think the real life example was fun and was a good chance for us to like discuss this thing. And then the equations were nice and simplified. It was a good presentation. I feel like I understood it, knowing nothing about it.
Really? I think you're from material science.
No. Definitely not.
I was like, wow, some expert in the audience.
I like the process, how you introduce this example. I like this part. I think it's quite interesting that in the blackboard you present the formulation of this, because normally when you see this in the presentation, sometimes it's amusing, I don't know how to say this.
Yeah.
And it's more, I can realize better when I see this, and I love the final sample. I think it's quite
And you had the drawing to go along with the equation, so it was good to like have something to point to on the board.
One quick thing is maybe you have labeled your x-axis as well.
Oh, yeah.
Like it took me like 2 seconds to think about what it was, but it didn't take me 2 seconds. So, but yeah.
Yeah, no, I think starting with the problem was a good idea. I think, for a group of novices, starting in with the terms like toughness and strain and stress, it's a little bit extraneous at some level, because I don't know, I have a material science background, so I mean I know what the terms are, but you guys don't. So whether or not you felt like you could really use those terms effectively, maybe you could have answered that question anyway, even before those terms. And I think throwing those terms in there could be a distraction at some level, like for this kind of a talk, right?
Yeah.
Just think about why they might have broken, and then you'd come up with temperature, and then you could talk a little bit about the idea of toughness, or about the idea of critical length or whatever. But you don't. I think the use of the terms might just it's just extra stuff to process that novices might not have a place for necessarily, and maybe trying to force it in there. But if you don't have the background for it, it's hard to do it. So, and then I think I would be a little bit careful about saying about the energy that people know, when something breaks, that this is an energy, where the energy is coming from, going to E positive, E negative, and then whether you said you were going to get into the fact that it was negative, W is negative, but there was a negative sign in front of W, but but what does that mean? So I think just being a little bit more aware of the level of the audience, so that you say what needs to get said, because it's a great story. I mean, you told a great story, but I think you added in some details that might have been potentially distracting for this purpose, right? So in a class, obviously, you're going to define the terms and all that kind of stuff, and there's a place for it, or the students would know what those terms were. But for this kind of presentation, you might want to think about what you have to say and what you don't have to say, right? Because it's obviously at a certain level anyway. You know, you've kind of told a story at a certain level anyway. So. But a great pace, a nice interaction with the class. You know, there was a good eye contact and good questioning and things like that, and that worked really well. So good.
Okay.